today, and I'll share my screen. So I don't know if I would call today's paper a paper, actually, because I was thinking if you submitted it to a conference or a journal, it would actually be very unlikely that it would be accepted because there's not a lot of novelty in this paper. There's essentially two techniques that they use, which you could argue are novel, but I'm sure that they've been used in one way or another before. It's almost more of a white paper for some interesting results. Although then that begs the question, because it's kind of like a white paper. It's a paper that's kind of similar to the GPT-3, because GPT-3 was like we trained a bigger language model. That was basically what it said. And then they had massive amounts of evaluation. And while this doesn't have massive amounts of evaluation, the paper is more about like the emergent behavior and the generalization than it is about the method. So I don't know what I would call it. It's something to think about, or if anyone has an opinion, feel free to voice it. But before we started, I thought I would just show some cool videos of what like the goal of this paper is. So, and before I do that, just like I used to do academic research in robotics, and so I know a little bit about the field. And there's a lot of like holy grails in robotics, but like in terms of a lot of things that we would like to be able to do that are quite hard. But one of the ones is just like having a robot that can accomplish a lot of different tasks. And what's crazy is that like when I started doing this type of research, a task would be something like you started a robotic arm from a specific position, and you had an object in a specific position, and the robot could accomplish that task. Like if you moved the object, like grab the object, that could be the task. If you move the object like 1 centimeter, when I started out, that was kind of considered a different task, which is a very different than how we define tasks as humans. But there's been a lot of progress since then. But even now, you'd be surprised what's considered like a task, and it's usually a lot more limited than what we would call, like we would consider a task as a human. But here, and so the point I'm trying to make is that tasks in robotics are much more limited things. And so one of the like big goals of all robotics is actually finding ways of generalizing to new tasks, whether that means that like you could shift the object around, or ideally you could ask it to do something completely different than it had done before. Like you taught it to push things around and grab things, and you could ask it to like balance the object on its end effector. But anyway, Leah, let's look at, and this paper is really about generalization, not necessarily in terms of tasks. They point out that this model can't do that, but in terms of a lot of the other ways that it's hard for a robot to generalize. So I'll make this full screen and press play. So here's an example of a task that's being performed, which is move the banana to the water bottle. And these are unseen tasks, which means that that the robot didn't see these instructions when it was being trained. And the interesting thing about these tasks is that if we go back, you can see it says put the strawberry. It's so fast. Put the strawberry in the correct bowl, which is like there's some semantic reasoning that has to happen here for the model that's being used to control this robot. So it has to understand that like the correct bowl is the bowl that has other strawberries in it. But when I say new tasks here, what I mean is that they're like a new set of instructions for the same kind of task. So this is like a pick and place task. It's been trained on pick and place tasks, but not on this specific one. Also, if you do robotics research, you see like there's so many failure cases. I'm sure this robot is pretty effective, but it could be that you like they did this maybe like 20 times to get the correct result. And a lot of the time, it's the fact that it was even able to do it that shows is the proof of concept in this type of research. So yeah, it's showing you a lot of examples of semantic reasoning in the task descriptions. It's pretty cool. And what is this one? That's a really long. Pick an object that is different from all the other objects. So it's able to understand that this is an object that's different from all the other objects. It's pretty cool. Okay, that one's not as interesting. And then the last one is, oh yeah, well, we can start going into the paper. But there's a lot of these tasks where you basically have a robot with a robotic arm, and what you're doing is you're asking to do different tasks where you might be pushing something or picking something up and moving it. Those are the kinds of tasks that it's trained on. And some of the generalization that happens automatically is that they move you don't always start in the same place. So the robot arm isn't like fixed, but there's a lot more generalization that happens. It's just not really obvious in the paper. Okay, so let's go to the paper. So this paper is RT-2 stands for robotics transformer, or probably robotics transformer 2, because there's a robotics transformer 1, and that's one of the like inspirations for this paper, in the sense that for robotics transformer 1, the authors collected this massive data set of massive by robotics terms of robots accomplishing tasks, where you have like you just have a really large data set. And so one of the issues with robotics is actually that data collection is very expensive, because you have to do it in human time. So because the robot like operates in the real world, you couldn't like parallelize it. So either you have like tons of robots, or you have one robot, but overall you have to collect data slowly. And I think it says it somewhere. It says like 17 robots. What is it? Months. Oh yeah. So the robotics data that was collected for this was collected with 13 robots over 17 months in an office kitchen environment. So basically, in like a specific room, they were collecting data for almost a year and a half to create this model. So that's one of the data sets that's used. And the other data set that's used is from like it's visual question answering data. So you can see it over here. Like what is happening in this image: a great donkey walks down the street. Something in French. Anyone knows French? But so they have these two data sets. One is robotic actions, and one is, as it calls it, like internet scale visual question answering. And kind of like the key insight of this paper, or the idea of this paper, is like, can we leverage this massive amount of visual text data for pre-training in order to create, or for pre-training and then fine-tuning, in order to create a model that can accomplish tasks, what's called end-to-end. So like usually the way that in the past, one way that these robotics tasks, like pick up a banana and place it on a Coke can, have been approached, is that you have like an upper level model that will like take a picture of the scene, understand that there's like a banana and a Coke can and whatever else is in there, and like then kind of say, okay, move. It will create a set of instructions like grab banana, move to Coke can, place on Coke can. And then below that, you have like a lower level controller that outputs like the actual actions that happen to the robot. So for the case of this robot, where is it? Do you guys know how to get rid of this? I think it's okay. There we go. For the robot, where is the actual? Okay, this is the set of actions that are. This is what an action looks like. So basically what this is saying is that if we go back to the video, you can see this part of the robot here, where my cursor is. That's called an end effector. And you can specify its pose in the 3D world with respect to some origin. Actually, these are all changes, so it doesn't matter. You can specify an action by saying, like, okay, move this amount in the X direction, this amount in the Y direction, this amount in the Z direction, which are just like Cartesian coordinates. And then you also have to specify rotation. So you can specify a change in position completely with these 6 degrees of freedom, given that you're in 3 dimensions. And then also, if you see here, the robot end effector has a gripper, so it's saying like how much should it be opened or closed. So these are pretty low level, what they call low level actions. You could go even lower level, but these are pretty low level. And so in the past, we've had like 2 layers of reasoning. One is like this upper level of reasoning, which takes instruction and creates a list of tasks to accomplish. And then below that, you have like something that takes these tasks and breaks them down into these actions. And so they want to create a model that can do the whole thing in one. So you give it a set of instructions, and it just outputs actions for the robot end effector in order to accomplish the task. I think the main reason why they want to do this is because it creates a much simpler model, and it's probably a lot simpler to train, because I could see how it could be more complicated, but like you just say like, okay, here's the input, and then here's the action that you have to take. So it's a simpler model, and maybe you could argue that because it's doing all of that, there's more room for generalization. I'm sure if we talked to one of the authors, they'd be able to give us some pretty cool reasons why that's such a good thing. But so they want to create this model that can take in instruction and output low-level robotics commands. And what they also want to do is try to leverage like the benefits of these web-scale data sets, as they say here, for improving the generalization of the model that they're training. So we can't have web-scale data sets for robotics because robots don't exist on the web. They exist in the real world. But we do have all these data sets that have probably like useful information for training a robotics model, because we have all of these data sets, like especially vision to text, that shows like semantic reasoning about the environment that you're looking at. And also there's the benefit that you see your model will see a lot more different images than if you than the robotics data that you're working with, because like the robotics data that we just saw, it was collected in a single room, and probably with not that many different points of view of the room. Maybe there was, I don't know. But so you see very little variation in robotics data sets. And that's just because it's hard to, like, it's not like, imagine how expensive it would be to like fly a robot to Everest and then fly it to like Atlanta, and then all the different places that you could think of that where you'd want this robot to operate. So it's just not very feasible. So they're saying like maybe we can leverage these web scale data sets for visual question answering, or for visual language models, in order to create a model that generalizes better to new tasks. Yeah, that's kind of the key idea of it, because the previous model, RT-1, it was just trained on robotics data, and So it was like pre-trained on robotics data, and so they saw how well it generalized. But this one, it's pre-trained on the web scale data set. So basically, you start out with a visual language model, which, sorry, let me tell you what a visual language model is. A visual language model is a model that can take in a series of text and images and output, and it can generate text. So it could generate like this description here: a donkey walks down the street. And there's quite a few of them. They use 2 different visual language models that are out there. Where are they? Yeah, PolyX and PalmE. I guess those are like the state-of-the-art ones that are used these days. So they start off their training with these 2. They train both models with both of them, but like essentially they start off their training with a model that's been trained on like a massive web-scale visual question answering data set. I think it's like it says like 10. It's like got billions of question answers, and then they have 2 things that they do that are like the novelties of their method. Okay, so the first thing is that they tokenize actions. So a token in, sorry, let me just find the right, so I'm not scrolling while I tell you all of this. Here it is. Okay. For text generation and processing text in general, a token is like an atomic unit of text. It could be like a space, or it could be a word like the. But basically, the way that text is processed in language models is that you get the text as a string, and then it breaks it up into tokens, which are like these atomic units. And then it will take those tokens and convert them into like token indicators, so an integer related to each token. And then within the language model, these become feature vectors. I think there's a good, yeah, here. So like RT-2 at the end, it outputs this sequence, which are token indicators. And then when you detokenize it, you get a string which tells you what actions to take. So the first innovation, which again, I don't consider this like something, this is definitely not something new, but it's also not like, it's probably never been applied to robotic actions, but applying to robotic actions doesn't seem like such a huge novelty. Maybe it is though, and I'm being too harsh. But basically what they do is they encode a robotics action as a set of numbers, like a set of integers, by binning actions. So like the change in pose, y, it's a continuous value from like negative infinity to infinity. And they essentially create a set of bins. So like bin 0 could be -1, and bin 1 could be -0.9, and so on. And then they output these, they convert actions into these integers, and then they feed this, they tokenize this set of integers in order to create labels of like image to action. And they do that by just recycling some of the tokens that are already in the vocabulary of these language models. For one of them, it's quite easy. For the other one, it's quite hard. But yeah, that's kind of like the question of how do we get the model to output both robotic actions and text. And that's by just tokenizing the actions and fine-tuning on these.
How can we understand that this really increases the data size, right? Because it's from what it sounds like is yes, you have this pre-trained model, but then you sort of redefine what the output of that model is supposed to mean. So how can the pre-training still be sort of relevant for the movement?
Well, I don't know if it's relevant for the movement, but I think the point is that it's relevant for understanding the instructions. And so because it's relevant for understanding the instructions, it can lead to better movement because the robot is able to like, or the model is able to, I don't like the word understand, but I'll use it, understand what the instructions are and then translate that into low-level actions.
But it somehow must relate to the the vocabulary sort of used at the robot data set, right? So the robotics data set, if they say if they were to make up their own vocabulary of what stuff means, you wouldn't expect this to work at all, right? Because then these would not be, yeah, would not translate, or yeah.
Yeah, I see what you're saying. It's like it's almost like you're asking it to output in a completely different language than what it was taught.
Yeah, so somehow it must make use of the robotics data being, at least to some extent, similar to the task that the larger model was trained on. No?
Yeah. To be honest, I'm not sure. There's an experiment which shows like if they didn't have the pre-training, how it would perform, and it performs worse.
Yeah.
But yeah, I think that I don't know. I do have this question about how valuable this pre-training is when you're doing something so different.
Yeah, because of course from the pre-trained data sets doesn't have any robotics movement as correct answers, right? So it's sort of, yeah, you wouldn't have any direct feedback loop between input and output there, and this sort of seems to suggest that this double training or fine tuning sort of would create a connection where there was none before, which is cool, which is a bit magic, right? But one wonders how it works.
Yeah, for sure. But these models are like so massive and so opaque that I think it's quite hard to figure that out.
Could it be working by reducing the size of the search space?
Possibly. But then again, because say we use the example of where the symbols are redefined. Now, the new input should translate to something that is not a robotics input, right? Because with highest likelihood it would output tokens that are not in those 256 tokens have been yeah.
There's an experiment, and we'll go back to this, where they're comparing like the previous model RT-1, which is a model just trained on the robotics trajectories, to their model RT-2 on seen tasks. So these are tasks that are seen like in the training set. And you can see that RT-1 performs about the same. Like RT-2 does perform a bit better, but they all perform about the same, which suggests that it's not like, I don't know if the fine tuning or their approach is improving the ability of the model to perform robotics actions. It's just improving its ability to deal with like new scenes or like new tasks. So to me, this experiment suggests that it's helping it with understanding the environment, its environment, like as opposed to like improving its ability to manipulate objects. And that's also probably supported by the fact that the robot doesn't learn how to perform any new skills. So it can only perform the tasks it's seen in its data set. It can't perform a new one based on this pre-training.
Perhaps what happens is that certain elements like kind of code or so all get internally translated into target, right? So that the model doesn't know what kind of code is, but it knows it is the target for this task. So maybe that is where this generalization sort of happens.
Yeah, could be something like that. But so the whole point of figuring out how to express actions as text that can be tokenized is that now you can take these visual language models that have been trained to answer like to do question answering, like what is happening in the image, like they're pre-trained on that, and you can also take the same model as is without any additional architecture or anything, and you can have it output robotics actions. So that's why they do that, so that they can just use any visual language model and output robotic actions for it. But the second thing is that they have to, besides that, the second novelty is that they have to fine-tune this model, because like as Arvid pointed out, there's no like robotics manipulation tasks in the pre-training data set. And so as we saw before, RT-1, it actually uses just robotics data for fine-tuning. So just using robotics data wouldn't actually be that much of a novelty, although using a visual language model as the initial model would be a novelty. What they do is they do what they call co-fine-tuning. So if we go back up to this picture here, they fine-tune their visual language model on a combination of the visual question answering data set that it was trained on initially, and then also these robotic action data set, like data points. I think it's something like in the experiments, they use 66% robotic action and what is it, 34% visual question answering. And in experiments, they show that that's actually an important element to the performance that they get. So yeah, I guess there's now that I've explained it, I realize there's three novelties here. Instead of using some other model, they use a pre-trained visual language model as the initial model for this task. Novelty one. Novelty two is that they figure out a way to tokenize these, to turn the robotic actions into strings and then tokenize them so that the model can be trained to output robotic actions. And then they do this co-fine-tuning where they fine-tune the model on a combination of robotics data and also data from the visual question answering data set that it was originally trained on. Yeah, and so what that does is, I mean, let's talk about what the results are of training that way. Where should I start? I'll start with that chart that I was talking about before. I do want to go straight into it, but I did want to point out something that I was like, oh, well, this is a major issue with this paper, in my opinion, is that, so they're using these massive models to train robots and to perform actions, and a forward pass through that model, or when you're generating text is actually multiple forward passes. That takes a while, and if you think about, I think a lot of robots operate at something like, if they can operate at 50 hertz, or what seems normal is something quite quick. So you do multiple actions per second. But when you have these massive models that you're using to control them, that creates a massive bottleneck for controlling them quickly. And so they said that they had to deploy a multi-TPU cloud service and querying the service over the network. So they had to create quite a specialized system just to be able to run these models fast enough at inference time to use them. And they were able to achieve frequency of 1 to 3 hertz, or for smaller versions, 5 hertz. And that's why if you looked at the videos, they were sped up by 2x or by 4x. So I could see that that's actually a major limitation of this for applying it to real robotics, unless you're okay with robots operating at much slower speeds than humans do to perform tasks. Anyway, so let's look at this first table and talk about what the claims of this paper are, what the results show. So like we said, the robot is trained on a set of tasks, and then what they're really arguing is that the value of this type of using the pre-trained model, tokenizing the text, and doing this co-fine-tuning is that the model generalizes much better to unseen tasks. And they have 3 types of unseen tasks, which are unseen objects, unseen backgrounds, and unseen environments. And then they have seen tasks. So there's examples of all 3. So here are examples in A of figure 3 of unseen objects. So objects that weren't seen in the training set. Then for B, you can see examples of unseen backgrounds. And then C, you have it like examples of unseen environments. So unseen backgrounds and unseen environments seem a little bit similar to me, but I know what they're going for. Like these were probably all performed around the same table, which is why you see the same table there, with a different texture, or maybe they like change the table, but it's like in the same room, in the same place, and that's what an unseen background is. And then an unseen environment is they like literally move the robot around. So they put the robot near a desk, or they put it near a kitchen sink, and they ask it to perform tasks. And they compared their model to like 3 previous models that claim to be able to generalize well to new settings. And you can see their performance, where the y-axis is completion rate. So you can see on seen tasks, they already say RT-1 is like the second best performing model base. It's like state of the art. So like they don't perform that much better, if at all, on seen tasks. But when when you get to, so their 2 models are the blue and the green. When you get to at all types of generalization, they always perform better. And again, with RT-1, most of the time doing second best. But so yeah, the point that they make is that they're able to generalize a lot better. So it shows that their model has a better understanding of like how to take instructions, connect it to the image that they're seeing, and like come, as Arvid pointed out, like come up with targets. So they did that experiment to show that it generalizes to unseen objects, backgrounds, and environments a little bit better. One thing they did, which I thought was like, oh, I'm really glad you guys did this. I think this makes a lot of sense, is because this task that they're evaluating the robot on is not something that's replicable. It happened at DeepMind in their office with a specific robot. So you'd have to buy that robot, which probably cost tens of thousands of dollars, and be there to reuse that data that was used. So instead, they actually create like an open source language table benchmark, which is like, it's essentially a much simpler task that can be run in simulation. And they use their method there, and they show the results of their method being used there. And you can see in this simple example, they have like they perform like 10% better in terms of completion rate than the other models. So I think it's just good that they chose to provide performance metrics on a task that everyone could, like this means that this research can be furthered. So that was good. They also did it on like a real world version of it, which is their real world out of distribution language table environment. Okay. And then we'll just, before I go on to talk about like the different types of more interesting behavior that they saw from the model, let's just talk again about those 3 things that we were talking about before, and how the different types of techniques that they used were important. So they took their model, RT-2, and they compared it. They compared its performance in terms of like training a model from scratch. So the red one is if you just trained a model, but you didn't use pre-trained weights as your starting point for fine tuning. You just did the co-fine tuning. So essentially, it's not a pre-trained model. You're just using the same architecture as the visual language model. Then you have the fine-tuned version, which is just fine-tuned on the robotics data. And then you have the co-fine-tuned version. And the like light versus dark color is different number of weights. So the light color is 5 billion parameters, and the dark color is 55 billion. So you can see that like the larger the language model, visual language model used, the better performance you get in all cases when you're doing co-fine tuning. And also the other thing they pointed out is that like they got such bad performance from the model that wasn't pre-trained that like they didn't even evaluate the larger version of the model. So yeah, that just shows that it's a good way of justifying the design choices they made for the method that they're proposing. That you need the pre-training, you need the co-fine tuning if you want best performance, So yeah, those are just some ways of, and then also that bigger is better. So the larger the language model you use, the better it is. Actually, it's not completely true, but we'll go into that in a second. Okay, so we talked about performance in terms of generalizing to new environments and all of that. But the other thing that they point out is that this model has a number of emergent behaviors which are really interesting, and they categorize those as symbol understanding, reasoning, and human recognition. And I don't know if they give examples here or further down. Okay. One sec. Okay. So here's examples of the different tasks that are which they consider emergent behavior, because they require like semantic understanding of the text instruction and then combining it with the image that you see. So it says, move the apple to the cup with the same color. So the robot has to understand that the apple is red, the cup is red, and that it has to move it there. Move the banana near the sum of 2 plus 1. So it has to do some math before it can figure out what to do. They have a different language that they use. And they say, like, pick a healthy drink. So I guess it has to pick water. Water bottle looks empty to me, though. Anyway. And then you can see, so this is a form of emergent behavior. The robot definitely wasn't trained on these, but it's able to actually accomplish these tasks because of co-fine tuning. And then they have other ones like symbol understanding. So move Coke can near Y, so it can move the Coke can near Y, or move banana to Android. I thought that one's interesting because it's like the model knows what these symbols mean. And the last one, which I can understand from maybe like a point of view of we're starting to really discuss the importance of the interaction between humans and robots. But in terms of, I didn't understand why it was super important that they did this one, as opposed to like, how is symbol understanding different than human recognition? I'm not sure. But anyway, it's like they have like move Coke can to Taylor Swift. So I guess the robot knows who Taylor Swift is. Or move Coke can to person with glasses. So these are all emergent behaviors of the robot that you can ask it to perform these tasks.
You have a comment here.
Yeah.
Can we do that before we continue?
Yeah.
Well, what if you mix languages? For example, the place of the apple a la gauche of the banana. Yeah. Funny.
Yeah, I'm pretty sure it would break based on my gut intuition and nothing else. But yeah, I think it's too far away from what it's been trained on. But maybe it would accomplish the task still. So yeah, there was also a number of emergent behaviors that they tested, and there's where is it? And here's like the performance of different models based on the different here are the different models. So one big thing is that the blue one is 5 times larger than the green one. And you can see in terms of symbol understanding, the blue version of the model they're proposing did a lot better. In terms of reasoning, they perform about the same. One interesting thing that they said is that, like, for some reason, the smaller model was better at doing math than the bigger model. But overall, like there was a combination of tasks that it was asked to do, and they perform about the same. But that the green model, like the blue model, was worse at performing math, and the green model was better at performing math. To me, that suggests that we don't really understand what's going on under the hood of these models. Like, because it's not a consistent relationship. Like, why is a smaller model better at doing math than a bigger model? Anyway, but yeah, again, you can see that, like, if you compare, all of the baselines have no more than a 20% completion rate, and then the larger model has at least double that. So it's like 2 to 3 times better in terms of this emergent behavior. So yeah. Oh, and then the last thing that they they evaluated is can RT-2 exhibit signs of chain of thought reasoning similar to visual language models? So they augmented their data set by creating these things that are like instruction. I'm hungry, and then you ask it to plan, and it says like pick up chocolate bar, and then you give it the action to perform. So this is a chain of thought thing where they have one model or the same model. What it does is first it performs a planning step, and then it performs like an action step. This chain of thought is probably pretty, maybe if you've worked with language models before in your job or in your research, this happens a lot where they like sequentially call the model, and essentially ask it to like break down a task into multiple steps. So they're just showing that it actually does improve performance and allows it to do things that are like more like here's a really ambiguous task, like I'm hungry, and then it's able to do things like figure out what to do and then actually translate that into actions. I don't think they have any results for that. I don't think they have any results for that. But they do show some things that are interesting. It's like, given blank, I need to hammer a nail. What object from the scene might be used? And then the planning is like, okay, you should use a rock, and here's an action. So it's just to be able to do more complex reasoning and translate that into action. So yeah, I thought it was an interesting paper. Don't have any. Is there anything else? Yeah, I guess they point out that the main limitation is that it can't perform new skills, and so that's something that they're going to look into later. And I said like maybe what we'll do is we'll try to introduce data, like it says new data collection paradigms such as videos of humans, which back when I was doing research in robotics was something I heard a lot of people thinking about, which was the idea that we have massive amounts of videos of people accomplishing tasks on the internet. Can we leverage those somehow to train robots to accomplish these tasks, even though robots aren't humans? So I think that's a pretty interesting direction forward. And one irony of the limitations, I thought, is that they say there's also another current limitation is that there are a small number of generally available visual language models that can be used to create RT-2. We hope that more open source models will become available, and the proprietary ones will open their fine-tuning APIs. I was like, yeah, that makes sense. But they didn't make their models openly available. So I don't know, if you're encouraging other people's whose work is like creating visual language models to make their models open source, then shouldn't you also make your model open source, or maybe not? I don't know. But that was something I was thinking. But yeah, that's the paper. Maybe some like interesting and simple insights that led to some really cool results. Yeah.
Peter, there is a conversation going on in the chat. If you want to comment, I'm not sure there is much to add, but have a look.
Okay. I guess I'll stop sharing my screen.
Yeah.
Okay. So the question is, what happens in foggy or low light environments or environments with a lot of background noise? All of those are really big issues for robotics. Like, I remember once when on like the first paper I was working on, you could put like a small black square on the red background that the robot was looking at, and it would completely break the policy that it was being used to control the robot. So I don't think it's that bad anymore. We have like a lot of things we do that make them more robust to this kind of stuff, but it's not that much better either. So yeah, changes in an environment can have like massive impacts. It's almost like those adversarial attacks that you see where, you know, like, have you guys ever seen the examples where they say, I'll just finish this and then I'll ask. Have you ever seen that example where they show you like a grasshopper or a praying mantis, and then they do an adversarial attack to make the model classified as a giraffe, and it looks exactly like a grasshopper still? I feel like maybe fogginess or something like that could cause the model to have the same thing. what are ways? So the question is, what are ways to make robots more robust to black square problems? Changing up the environment or introducing noise into your background. So if you artificially introduce noise, you can kind of get the visual model that you're using to, which is a common technique in computer vision anyway, to be more robust to changes in background. It's just hard because it's a lot easier to collect like computer vision data than it is to collect robotics data, because again, you have to do it with a real robot. Yeah, exactly. Yeah, so that's the paper. Does anyone have any other questions or things they want to say about it?
Just one add-on from this. I heard someone saying that you can detect the this computer vision problem or those some types of attacks on it by filtering out some kind of high frequency. So the grasshopper that looks praying mantis that suddenly looks like, you make it, answer as a panda. It's if you can there is some kind of defense against it that way. I don't know how good the defense is. But.
It's an interesting approach. I have seen in like the computer vision and then even in robotics, like using these primitives, which do some kind of like Fourier analysis on things. So maybe that's something we'll see in the future.
Yeah.
Cool. Well, thanks everyone for coming to Paper Club today.
Thank you for presenting. Good paper.
Thank you very much. Interesting, yes.
See ya.
Bye-bye.